Hello everybody, welcome to the Ultimate Physics channel. The topic of today's video is Michelson Morley experiment. The Michelson Morley experiment is one of the most famous experiments of the 19th century, which was performed by Albert Michelson and Albert Morley in the year 1887 to prove the existence of a hypothetical medium called ether, which could be established as a universal frame of reference. The idea of this experiment was to measure Earth's motion through the ether, that is, Earth's drift velocity through this hypothetical medium ether, and that would help to establish it as a universal frame of reference. This experiment uses an instrument called Michelson Interferometer, which had originally been designed by Michelson during his PhD, and he had performed an original experiment using that device in the year 1881 to measure the Earth's drift through ether. Michelson was awarded the 1907 Nobel Prize in Physics, the first American to do so, for his work in this experiment as well as for his accurate measurement of the speed of light, which is one of the most accurate values for the speed of light in those days. Now let us proceed to discuss this experiment in more detail, but before we do that, we should first understand that what was the need to establish ether as a universal frame of reference. So let's first proceed to discuss that. Let us discuss the need for ether. There are several reasons why scientists of the day pursue the idea of ether very seriously. For example, first, the idea of light as a wave had been firmly established after wave theory of light, and several experiments had been performed to prove different properties of light waves. So light as a wave had been firmly established by then. Now waves require a material medium for propagation. That was the idea that existed there. All mechanical waves require a material medium for propagation, such as, for example, sound waves, water waves, seismic waves. So all waves known then, all were mechanical waves and they all required material medium for propagation. So it was natural for scientists to believe that light being a wave must also require a material medium for propagation. So they were looking for a material medium in which light could propagate. So one such medium was considered to be the hypothetical ether medium. And Newtonian ideas of frames of reference for an object's motion was required, and therefore the motion of an object in different frames of reference could be understood using the Galilean transformation equations. So they thought that such an idea of frame of reference must exist. So ether could be fixed as a frame of reference, and the motion of light in different frames of reference could be studied using Galilean transformation equations, because if motion of light in the ether frame of reference is understood well, then it is possible to understand the motion of light in any other frame of reference with respect to the ether frame of reference using the Galilean transformation equations, thereby establishing ether as a universal frame of reference. That was the idea behind the Michelson Morley experiment and other such experiments those days. But one of the very important reasons for the Michelson Morley experiment was Maxwell's electromagnetic theory. Maxwell had proposed his electromagnetic theory and he had given a set of equations, and one of the important ideas of the Maxwell's electromagnetic theory was the light was an electromagnetic wave and it traveled with a constant velocity in a medium. And the velocity of light wave, unlike the mechanical waves, depends on the electrical and magnetic properties of the medium. Because for mechanical waves such as sound wave, the speed of the sound waves in a medium depends on the elastic properties of the medium. So, better the elastic property of a medium, faster the sound waves could travel in such a medium. Whereas Maxwell's theory states that the speed of light, for example, in free space is equal to 1 over square root of mu naught epsilon naught, where mu naught is the absolute permeability, that is permeability of free space, and epsilon naught is absolute permittivity, that is permittivity of free space. So this indicates that the speed of light in free space is equal to 1 over square root of epsilon naught mu naught, that is electrical and magnetic parameters. So the speed of light waves therefore would depend on the electrical and magnetic properties of the medium rather than on the elastic properties of the medium, which was not a commonly accepted view those days. So people wanted to prove and study ether and study its properties, be it electrical or magnetic properties or its elastic properties. Therefore, scientists of the day hunted looking for this hypothetical medium called ether. Now let us proceed to discuss the Michelson-Morley experiment in some detail. Let us discuss the experimental details of the Michelson-Morley experiment. The original experiment was performed in the year 1881 by Albert Michelson. This experiment was performed in Germany when he was a postdoctoral researcher there, and this experiment was considered to be not so accurate. So when he came back to the United States, he performed the much more sophisticated version of the same experiment in the year 1887, in which he collaborated with Albert Morley, and this is the now famous Michelson-Morley experiment of the year 1887. So the experimental details of the original 1881 experiment and the 1887 experiment are nearly identical, just that the 1887 experiment is much more sophisticated, producing more accurate results. Let us now discuss the details of the experiment. Light from a source is made to fall on a beam splitter, which would partially reflect the wave and partially transmit it. Both the reflected and the transmitted beams are made to fall on mirrors M1 and M2 respectively, and then again these two beams are combined and they are received at the telescope of the interferometer here at T. Now a compensator, which I have not shown in this diagram, is another glass plate that is kept in the path of this reflected beam, so that the light beam travels equal distances through the air as well as the glass medium. Because this particular wave that is transmitted through the beam splitter goes through a thickness of glass, therefore if you have an identically thick glass plate as the compensator along the path of this reflected beam, then that would compensate for the difference in thicknesses of the two beams. Here, the direction of motion of Earth through the hypothetical ether medium is in this direction. That is, Earth goes around the Sun, so its direction changes throughout the year. So at any given instant when the experiment is performed, if this direction is the direction of Earth's motion, let us say with the velocity v around the Sun, Earth is moving with the velocity v, this arm, let me call this as the OQ, parallel arm of the interferometer is parallel to this direction of motion, whereas the other arm, OP arm, is perpendicular to the direction of motion of the earth through the hypothetical ether. In an interferometer, when two such light beams are combined, there is a chance that an interference pattern is produced. If two such beams traveling with equal path lengths, they are combined at the telescope, an interference pattern is produced if there is a phase difference between the arriving waves here. Now, how to create the phase difference? Obviously, the first way to create a phase difference is to have a path difference. But if the path lengths are equal, the optical lengths traveled by the light beams, then here at different points on the screen, the waves would arrive at different times. So a time difference in the arrival of waves also would cause a phase difference of the waves, thereby producing an interference pattern. So typical interference pattern would have fringes, bright and dark fringes, equally spaced, right? So these are dark fringes and these are the bright fringes. So this is a typical interference pattern that one would see in such experiments. So now what was Michelson expecting to find? He didn't just expect an interference pattern, but he was expecting to observe a shift of this entire fringe pattern. So with respect to a reference point, he was expecting a shift of the entire pattern either to this direction or towards this direction, depending on whether he oriented the interferometer, he rotated the interferometer in this direction or this direction. So Michelson was expecting that a 90-degree rotation of the interferometer, that is the parallel arm becoming the perpendicular arm and the perpendicular arm becoming the parallel arm, would cause a significant fringe shift of the fringes of the interference pattern. So this was the shift that they were looking for when they performed the experiment. In fact, this was the shift that originally Michelson also observed in his 1881 experiment. So now the basic question in the interferometer experiment would be, how do we get the fringes here? Is there any difference in the optical path lengths between these two beams? So we set it up in such a way that, let us say that this path length is L1, OQ, and this OP is, let's say, L2. In the original 1881 experiment, L1 and L2 were taken to be equal, and this was around 1.2 meters in the interferometer of the 1881 experiment, the original experiment. If these optical path lengths of both beams are equal, then what causes the interference pattern here? Basically, because of the motion of the earth around the sun, the parallel arm, the path length remains, let's say, L1, whereas for this perpendicular arm, as earth moves, the mirror one shifts towards the right. That means this perpendicular beam is no longer traveling in this direction, it has to go like this to hit the mirror. This is a bit exaggerated, but this is the actual way the beam travels. So if you have to modify, this distance gets changed. So let me just try to write some equations for this. This one changes, let's say, so I call that as L1 prime. That would be equal to L1 plus Vt. Why I write Vt here? That is because the whole thing moves with the velocity v in a time given time t. The distance moved is from this point to, let us call this point as P prime, that is Vt. And therefore, the beam splitter as well as mirror M2 both would shift by that amount. So in one direction the path is going to be for the onward beam L1 plus Vt. But this beam gets reflected at mirror M2 and comes back. So effectively that would be So the combined total path length is 2L1 for the parallel beam. But for the perpendicular beam, this length is, let us call that L2 prime. This is L2, let's call double prime. L2 prime is going to be square root of L2 squared plus V squared T squared. This distance Vt. And L2 double prime is going to be equal to, again, L2 squared plus V squared T squared. That is this distance. Now, if you combine this, we are going to get L2 prime plus L2 double prime is equal to 2 times the square root of L2 squared plus V squared T squared, and this clearly establishes that the distances traveled by the parallel beam and the perpendicular beam, they are not equal. That is, the optical path lengths for these two beams are different, and therefore the waves arriving from these two beams are not going to be arriving at the same time at the telescope, and this would cause an interference pattern. So this is the first basic requirement in such interferometers, that you see an interference pattern because of the time differences and phase differences between the waves arriving at the telescope. So this is a basic expectation in any such interferometer, so there is no surprise in it. But what another important property that Michelson and Morley wanted to observe is the shift of the fringes, and that is caused by the rotation. So now I am going to show through calculations how such a rotation of the arms of the interferometer would cause a fringe shift, and calculate how much is the fringe shift they expected for this experiment. Let's proceed to do that. Let us proceed to do the calculations. Let T1 be the time for the parallel beam to travel between O and Q and back. That is from Q to O again. So let me call that as T1, and that is equal to the distance that it travels, that is the forward beam from O to Q, is L1 over that is the direction of light beam is this way, that is C, and the direction of Earth's motion is in the same direction V. So according to Galilean transformation equations, the velocity of this light beam would be added with the velocity of motion of the Earth. So if light was moving through a hypothetical medium ether, then the resulting velocity according to Galilean transformation equations would be C plus V for this beam, whereas when it returns, its velocity would be C minus V. So that time, the time is L1 over C minus V. So the total time for the beam, that is a parallel beam, that is the beam traveling parallel to the direction of Earth's motion through the Sun, that is going to be L1 over C plus V plus. Please remember that the fringe shift in this experiment is caused due to the rotation of the arms of the interferometer. Therefore, we have to calculate again the times for the travel of the light beams along the parallel and the perpendicular arms after rotation. So after rotation of the arms of the interferometer, what are the times? I am going to try to calculate. So let me say that for the parallel beam now, the time is T1 prime. This is going to be equal to L1 over, now since this became the perpendicular arm, now the velocity for this is square root of C squared minus v squared. So again it is L1 square root of c squared minus v squared. Therefore now this becomes 2L1. See, if you take it out, square root of 1 minus v squared over c squared. Whereas for the other arm, this is going to be T2 prime, that is L2 C plus V plus L2 over C minus V. That is, this is now the parallel arm. For the parallel arm, this is going to be 2L2. So try to directly write this. C 1 minus V squared over C squared. Right? Now, therefore, if we calculate the time difference here, let me call that del T prime. That is going to be T2 prime minus T1 prime. That is going to be equal to 2 over C is common. So L2 1 minus V squared over C squared minus L1 over square root of 1 minus V squared over C squared. So from these two equations, I can get the fringe shift by taking a difference of these two time intervals. So del T prime minus del T would give me commonly 2 over C, and then the first term L2 over 1 minus V squared over C squared. Then here I can take the corresponding term, that plus L1 over 1 minus V squared over C squared, and then minus this one. So minus L1 over square root of 1 minus V squared over C squared, and then this one minus of minus would become, this one would become minus L2 over square root of 1 minus V squared over C squared. Now if we combine these terms, you would get del T prime minus del T is equal to 2 over C. Then these two terms, L1 plus L2 over 1 minus V squared over C squared minus, again these two combined, L1 plus L2 over square root of 1 minus V squared over C squared. Now this can be, these two terms can be expanded binomially. Therefore, I can take that L1 plus L2 outside. So 2 L1 plus L2 over C 1 minus V squared over C squared power minus 1 minus 1 minus V squared over C squared power minus half. So I'll write the binomial expansion for these two expressions here. So del T prime minus del T is equal to 2 L1 plus L2 over C. The first term binomial expansion is 1 plus V squared over C squared. Of course, there are additional terms which we are ignoring. Minus, again 1 plus V squared over 2C squared plus the additional terms. So this is the binomial expression for these two expressions here. So this can be simplified as del T prime minus del T is equal to 2 L1 plus L2 over C. The first two terms will cancel, so the second terms, if you do simplification, that is going to result in another V squared over 2C squared. And in the original experiment, L1 was equal to L2 was equal to, let us call that L, which was equal to, of course, 1.2 m, 1.2 meters. In the 1881 experiment, so del T prime minus del T is equal. That would be 2 into 2L over C, V squared over 2C squared. So these two tools can be cancelled. So effectively what we have here is 2LV squared over CQ. So the time difference here in this case for the rotation is 2LV squared over CQ. So we've got so this is the expression for the difference in time differences for the interferometer when the arms are rotated. So I already mentioned that in the 1881 experiment, L was taken to be 1.2 meters. V is the velocity of the earth around the sun, that is 3 into 10 power 4 meters per second, or 30,000 meters per second. And C is the velocity of light in free space, that is roughly taken to be 3 into 10 power 8 meters per second. So if you plug in these numbers here, we would get 2 into 1.2 into square of V is 9 into 10 power 8 over cube of this is 27 into 10 power 24. So this would entail 2.4 over 3 into 10 power minus 16 or 0.8 into 10 power minus 16, which would be 8 into 10 power minus 17 seconds. So this is the difference in times for the rotation. Now what is the time period of the wave? We have to calculate. Not for the fringe shift to be calculated, we have to calculate the time period of the wave. So we have a simple expression for the velocity of a light wave, that is a product of its frequency and wavelength. Wavelength in this case was originally Michelson used a sodium vapor lamp for setting up the experiment, but the actual experiment was performed using white light. So for this particular case, one can take the wavelength to be approximately 6000 angstrom. So if I take lambda to be 6000 angstrom, then my time period would be, my frequency would be first C over lambda, and therefore my time period T would be inverse of this, that is lambda over C, and that would be equal to 6000 angstrom is 6 into 10 power minus 7 meters over the velocity is 3 into 10 power 8 meters per second. So the time period would turn out to be 2 into 10 power minus 15 seconds. This is the time period of the light wave. Therefore, the fringe shift can be calculated as del t prime over del t prime minus del t over time period t, that is 8 into 10 power minus 17 over 2 into 10 power minus 15, which turns out to be 4 into 10 power minus 2 or 0.04. So this is the actual fringe shift that Michelson expected in his original experiment of 1881. But when he tried to publish the results, scientists of the day advised him to improve the accuracy of his instrument and repeat the experiment. Therefore, when he came back to the United States, he collaborated with Albert Morley in what is now the case Western Reserve University, and they together performed the 1887 experiment, which is the same experiment with much improved accuracy. So in that experiment, Michelson and Morley used a number of mirrors for multiple reflections across each of the two arms. and this enhanced the optical path length from the original L is equal to 1.2 meters in the 1881 experiment to L is equal to 11 meters in the 1887 experiment. Further, in order for the vibrations to not disturb the fringes, they carried out the experiment in a different underground laboratory of that institute, and they also mounted the entire interferometer setup on a trough containing mercury, which would significantly reduce the vibrations, and therefore this improved the accuracy of the experiment by about 10 times. So the fringe shift for the 1887 experiment that they expected was around 0.4, and their instrument had high accuracy. But in spite of all that, even in the 1887 experiment, Michelson and Morley did not obtain this fringe shift. They did not obtain any substantial fringe shift. Therefore, they had to conclude that their experiment produced a negative result, and this negative result would mean that they understood that it was not possible to detect the presence of ether. That means there existed no hypothetical medium called ether in which the light waves would propagate. Several people tried to explain the negative result of the Michelson-Morley experiment. For example, Lorentz and Fitzgerald independently explained that the negative result of the Michelson-Morley experiment could be understood if one assumed that the lengths along the direction of motion contracted, and that would result in the negative result, null result for the Michelson-Morley experiment. Another interesting explanation for the negative result was the ether drag hypothesis, which was not possible if one has to account for what is called as the stellar aberration, commonly observed in astronomy. Apparent change of position in a circular orbit of a star as seen from the Earth, that cannot be observed. Therefore, ether drag hypothesis was also discarded. So all the efforts to explain the negative result of the Michelson-Morley experiment failed, and therefore it was conclusively proved that there existed no hypothetical medium called the ether. Though Albert Einstein never himself directly attributed the Michelson-Morley experiment to be a factor for his proposition of the special theory of relativity, one cannot deny the fact that the Michelson-Morley experiment did indeed play a very significant indirect role in the development of the special theory of relativity. Thank you.